Hey, good morning, good afternoon, everybody. Welcome to Free Teach. And today we're looking at allocation problems and using the Hungarian algorithm to solve this. So, keys here are we have a series of steps that are really helpful to us, and I've just popped them in a basic list just there. And these problems help us to assign tasks or values between two connection points in a bipartite graph. Okay, so what we want to be able to do is assign tasks so that the minimum time, distance, something like that is covered or taken to do something. Okay, where one element may take a various amount of time to do several other elements, and there are multiple elements that can do the same job or multiple jobs, and they must be assigned the correct task to minimize the time, distance, cost of something. All right, so first problem, easiest if we get stuck straight in. The first problem is four computers need to connect to 4 separate network nodes. The distance between each node and computer is given. Use the Hungarian algorithm to decide which computer should link to which node. Okay, so let's pop our, I'm going to put our computers down this side. A, B, C, D, and W, X, Y, Z. Alright, first thing we do is we subtract the lowest number from every row, from the values in every row. So from row A, I'm going to take 5, because there's my lowest number 5. From row B, I'm going to take 8. Row C is 8, and row D is 7. Okay, so I'm going to subtract those values from each of the 4 values in their specific row. So we end up with 5, 0, where's my brain gone? 8 and 11. Then across the next one, we have 0, 13, what do we got there? 6 and 1. Then we have 5, 9, 0, and the last one is 4 in row C. Row D, we're subtracting 7, so it's 0, 8, 15, and 0. Alrighty, so that's the first step. Next step, we do the same, but we do it to each column. Okay, so in each column, we subtract the lowest number. So in column W, I'm going to subtract 0, okay, because 0 is lower than 5. Okay, and that's one mistake that some people make, is they go, oh, 5's low, or a better column might be that we look at. If we look at column Z, some people might select 1 as the lowest number because it's the lowest positive integer, or their brain just stopped working, whereas 0 is the correct one to take there. So after we've done that, I'm going to take 0 from there as well. And I've got my cheat notes here because I made sure I did this problem earlier. And yeah, cool, on the right track. It's always harder when you're under the pressure of the camera. And 0. So we don't need to take anything from any of those. Okay. So subtracting the columns, nothing changes. And I'm not actually going to put in anything in there. After we've done that, we do a line check. So we see if we can cross every 0 in our, we see if we can cross every single 0 with the fewest lines possible. All right, so I can cross there. That's the only way I can get doubles in, really. Anything else is going to take 3 more lines to do. Yeah, so that's the fewest number of lines I can use to cross those zeros. You can have them configured any way possible, as long as it's the fewest number of lines. Now, the next part that we ask is, does the number of lines equal the number of rows? So we've got 4 lines, and we've got 4 rows. So that's a tick it does. Okay. Once we've got that, we can move to, probably haven't made that really explicit. So if the lines equal the rows, go to step 6. If the lines don't equal the rows, you go to step 5. We'll do a problem with that later. Step 6, allocate our problems using a bipartite graph. So A, B, C, D, W, X, Y, Z. Alrighty, so bipartite graph. So each 0 is an arrow. Okay, so the first one, I'll do this in a different color. For the first one, A has a 0x. Alright, so A can go to X. Then we have B has a 0 at W. C has a 0 at Y. And D has a 0 at W and Z. Okay, so now we need to assign those tasks. Now, even though Z has 2 tasks it can go to, we've got to realize that B only has 1 task it can go to, and that is the W. Right? So if B has 1 task, and that task can also be done by D, but D can do another task, then we have to assign the tasks that are best suited to each, vertice in our graph. All right, so A will do X, B will have to do W, C will do Y, and D will do Z. Right, now we can go along there and then put in our values of how much cabling is needed for these networks. So A to X, we go back to our original graph here. We don't use any of the values that we've manipulated. So A to X is 5, B to W is 8, C to Y is 8, and D to Z is 7. And then we can go and add them up depending on, as it says, use the values and sum of allocations to complete the question. So we've basically completed this question. Doesn't have anything really extra to ask of it, but what we could do, you might be asked to, what's the total distance of cabling, what's the total time maybe used, what's the distance that something's traveled. So total distance of cabling here is going to end up 8 and 8 are 16, 21, so we're going to have 28, and maybe that's meters. All right, and that is our Hungarian algorithm. Okay, now I'll go and do another version of that. I'm going to copy that because I didn't copy it earlier. Down to my next part, just so we've got the steps with us. And there. All right. So they're okay. Beautiful. All right, next one. In the eating competition, each team must select a member to eat one type of food. Based on the times given in the table, use the Hungarian algorithm to allocate who should eat what. Okay, so based on this, the shortest amount of time in an eating competition, the better we're off. Okay, so first thing we're going to do, I'll start writing in some. I've got a blue pen, I don't want to write in a blue background. So Alec, Jamie, Max, Alicia. Too many E's in Alicia, too many dashes in Alicia. And you can eat hamburgers, hot dogs, pies, or pancakes. Same steps as before. Subtract the smallest from each row. All right, so Alex taking 4 off, just there. Jamie's taking 9 off, and then Max is taking 5, and Alicia is taking 3. Okay, so I'll rewrite all those with a subtraction. So 4 off the first row gives us 11, 2, 7, 0. 9 off the second row gives us 9, 0, 8, and 1. Then we have 7, 0, 14, and 2. And last one we've got subtracting 3, so it's 10, 0, 11, and 3. So once we've done that, we've done our tick them off rows. Next is our columns. So we're going to subtract from the hot dog line. We're going to take 7, We're going to take 0, going to take 7, and we're going to take 0 there. All right, so let's put our AJME, H, HD, I, and pancake. Alrighty, so subtract those, so 7 from that column, which is 4, 2, 0, 3. Taking nothing from this column, so it stays the same. And we're taking, what do we got? 7, so that's 0, 1, 7, and last one 4. And we're taking 0 from the last one, so it's 0, 1, 2, 3. Alrighty, same deal as last time. Use our line tool. Let's get a different color than before. And see how we can cover this in the fewest number of lines. Okay, we're up to our line check in step 3. Okay, so sorry for messing through. So I'm going to have that one down there because my line tool is not working at all. Why didn't you give me a line? It's going to give me a red line this time, I wonder. So I've got a down there. I can go across. It isn't going to give me a one. Play this for another second until it annoys me. There we go. Then we go across there. That's 2. And then another one up there gives us 3. Okay, so as you can see, in this example, the number of lines, 3 lines, doesn't equal the number of rows, 4 rows. That means we haven't found a solution to our graph yet. Now, what that means is we go to step 5. Step 5, we subtract. So we find the smallest number not covered. Right, the smallest number not covered is 1. Right there. We subtract that from any uncovered elements. So all these 6 here, doesn't matter what configuration you have your lines in, you subtract it from all those elements. Then you add the number to any element covered by 2 lines. So when we say covered by 2 lines, we're going to add 1 to there because it's at the crosshair. So we add 1 and there. Add 1. Righty, and these ones are subtract 1 from all of those. Put our A, J, M, E in. And then our was it hamburgers, hot dogs, pies, and pancakes. Okay. Now it takes a little bit of concentration to make sure we do this right. I'll do the uncovered ones first, and I'm going to subtract 1. So that becomes 0, 6, 3, and then 0, 1, 2. Then I'm going to add 1 to this, 5 and 2, and the rest stay the same. 3, 0, 0, 0, and 0, 0 there. Okay. So it's handy if you've got a whiteboard to do this, a pencil. You know, you need a couple of them. You can do it. A pencil's good if you can need to rub stuff out. But now we're back to our line drawing. Okay, so let's jump in there. Got my line tool. Okay, the fewest. So I'm going to cross there. 1, 2, 3, 4. Okay, so the lines equal the number of rows this time. Now there's no way I can configure that to change it. So 4 lines equals 4 rows. Okay, so now we've found our solution. From there, we need to assign them using a bipartite graph. So we are going on. I'll do that side here. So we're going along. Go to A, J, M, E, and H. Alarms going off. H, HD, pi, and P. Better make that mathematical pi. So from there, draw our lines everywhere there's an arrow. Okay, so Alec can go to pies, pie, and can also smash the pancakes. Jamie goes to hot dogs, pies, and pancakes. So Jamie gets hot dogs, pies, pancakes. Max goes to hamburgers and hot dogs. Max goes to hamburgers and hot dogs. And Alicia goes to hot dogs. So now we have to assign them. It's a bit messy, I don't know. Oh, good. So we know that Alicia has to go to hot dogs, okay? No other choice. Alicia is hot dogs. And we know that Max has to go to hamburgers because no one else does hamburgers, even though Max does another thing. Right. Now the last two, Alec and Jamie, can either go to pies or pancakes, okay? Because you can see they both have, if I go across here, it's easier to see. They both have zeros there. All right. Now, what that means is we have two ideal solutions. All right, so let's put Alec on pies first and Jamie on pancakes. And then we're going to do the opposite solution of Alec on pancakes and Jamie on pies. And the other two can't change. And you'll see that it makes no difference to the allocations as far as the time in minutes in which it takes these guys to finish their competition. So going back to the original one, Alec pies is 11. Jamie and pancakes is 10. Max and hamburgers is 12. And then Alicia and hot dogs is 3. Okay, add those up. 11, that's 21. That's 21 and 12 is 33. That's 36. Now I've done something. We've got not added up here. 5. Not right. I feel like I've got H. So Max is hot dogs. What am I saying? Max is hot dogs. Have I got them out the right way? Max is hot dogs. Yeah, okay, that's cool. Okay, so 11, 10, 21, plus 12, 33, 36. And then we have Alex for pies. For pancakes this time is 4. Jamie for pies is 17. Max 2 hamburgers is the same, so it's 12 and 3. And we get 21, and then that's 33, 36. So you can see, sorry, I've done a miscalculation on my previous notes that I hadn't checked, but this is all right now. So regardless of which combination that you make with the top two, you get the same result in the end. Okay, so that is who should eat what. And that's the Hungarian algorithm done a couple of times. Follow those steps. The key is to, I guess, know that your zeros are the lowest number in a couple of cases. Be clear on your line checks. Okay, it is the fewest number of lines possible. Okay, so over here when I get 4 lines, that is the fewest number of lines I can do that in. And when you're going back to subtract the uncovered and then add to the multiple covered ones in this step here. Just be careful with that. Then finding your unique solution. Generally, that's about as complex as I've seen them. I mean, there's sort of arrows still going all over the shop there. They don't get any more complex than that. And it's more that it's maybe on the screen. So hopefully that helps. If you've got any comments, pop them in down there somewhere. Like the video and subscribe to the channel, guys. Happy days. Hopefully, this is hitting you in a place where you're happy and getting through everything you need to. See you next time.